Thanks again for inviting me. Hello, everyone. I'm Nick Banks, a software engineer at Microsoft. I'm on the data path and transports team, which is responsible for most of the networking stack from the IP layer up to the sockets API. We're part of the core OS team in Azure. Provides the OS platforms for all of our products on Windows, Xbox, pretty much everything that produces an OS. Also, by the way, I'll take questions at a halfway point and at the end. I've got a lot of slides, so I'll split it up in half to allow people to get some questions out. I get the chance to work with a lot of internal teams and external groups to help adopt and deploy various QUIC-based solutions. Because of the ability for QUIC to deliver both reliable and unreliable data securely and efficiently, QUIC's generating a lot of interest from a lot of different groups. I'm personally responsible for QUIC, our open source cross-platform QUIC library. It is used for the basis of pretty much all Microsoft products that use QUIC besides Edge. Edge obviously using the Chromium stack shared with Chrome. As I already mentioned, I work with a lot of different teams and kind of responsible for the base QUIC usage for most things at Microsoft. Few things right here that use QUIC and that we've shipped QUIC support in. The latest version of Windows Server and client both have QUIC inbox support to support HTTP and SMB scenarios. Microsoft also released .NET 6 with preview support recently for HTTP3 on both Windows and Linux. In the open source community, we've had a significant amount of interest in DI, visuality, even some large media companies such as DreamWorks have started looking at usage or have actually deployed usage of QUIC. We'll come back to QUIC a little bit more later. Right now, we're going to look at Microsoft's biggest QUIC deployment, Exchange Online, and its HTTP3 usage. Just to make sure everyone's on the same page, Exchange Online is the server side of Outlook email app that's accessible from many different desktop, browser, and mobile clients. When you're looking at this from a network perspective, Exchange usually uses long-lived connections, periodically send out, on average, about 8 kilobyte request size, and get a varied response, usually between 2 and 32 kilobytes. Like I said, one key thing here is that they are long-lived connections. I'm going to go through the latest data we have for both HTTP2 and HTTP3 so we can compare and contrast them. In the last few months, we've deployed the latest Windows Server with HTTP3 support to over 30,000 servers worldwide. On the slides, you can see the overall usage between HTTP3 and HTTP2 on Exchange servers from all Outlook clients. So this is all clients hitting Exchange. This is essentially the data we have for last month. HTTP3 currently peaks at about 500,000 requests per second, while HTTP2 goes sometimes well over 2 million requests per second. In the next couple of slides, we're going to look at the data specifically for the Outlook web app, or the OA client. This is the client that runs in the browser when you navigate to outlook.office.com. The reason we're going to look at the data there is because the browser was our target first client, since we have quite a lot of usage there and the browser already supported HTTP3. As I just mentioned, this data comes from the browser OA client and does not include any mobile or desktop clients. Additionally, we're only going to be looking at data from servers that have been updated to the latest Windows server. These are the ones that support HTTP3. Goal here is to try to make an apples to apples comparison for servers that support HTTP3. Let's look at all their HTTP3 requests and their HTTP2 requests. Those deployments also have updated telemetry in the OS that allow us to get a better view of the data. Looking at the data here, this chart shows the daily sample usage of both HTTP2 and HTTP3 from OA clients. As you can see, it's really quite even. And on the weekends, HTTP3 goes a little higher, though on average, HTTP2 might be a little bit higher. And again, this is last month, and every day it changes a little bit. One immediate takeaway here is that there's a significant client population out there already that is capable for HTTP3. So any new services out there that onboard HTTP3 support will likely immediately see a large percent of their traffic using HTTP3. In the next two slides, we're just going to take a look at a breakdown of the data in a couple different ways. On this slide, we can see the HTTP usage is evenly split between Chrome, which I believe includes Edge, and other browsers. Still working with the telemetry team to see if we can break this down further. But as you can see, independent of the browser, HTTP usage is pretty much the same. So there shouldn't be any browser bias in the data overall based off of usage at least. Now on this slide, you can see very similar usage independent of the IP version and even the region. Maybe the somewhat notable differences that HTTP3 has slightly more IPv6 usage, just slightly, and has relatively less usage in Latin America and Asia Pacific regions. But still, overall, there's not really any significant difference here. And again, hopefully should be no bias in the data one way or the other here, because it's about as apples to apples as you can get when you have a large scale deployment. So the key takeaway from the last couple slides is that the OA clients are generating pretty much a dead even split of HTTP2 and HTTP3 requests, and the data does not seem to have any bias to any scenario. This gives us a really great opportunity to compare HTTP2 and HTTP3. This apples to apples comparison allows us to directly compare the request latencies for each HTTP version, is what we'll look at in the next couple slides. Before we look at the actual data, I just want to essentially provide a definition here. So OA uses what it calls the last mile latency when comparing and analyzing latency data. So last mile latency is essentially the total latency subtract the backend processing time. As you can see from this little diagram, everything in green is considered the backend processing time. The goal here is to try to just get a latency number that is focused on the last mile, the hop between the client and the front end server, to analyze things like network costs. So that's going to be all the data we look at from here on is last mile latency. So for the next couple of slides, we're going to be looking at data from the last week or so, which is made up of about 500 million samples for each HTTP version. So a pretty good sample set here to hopefully draw some useful conclusions. These two charts are breaking down the last mile request latency by HTTP version and showing various percentiles from P50 up to 4 nines. The chart at the bottom is the exact same data, just in the raw number form. The chart at the top shows the raw absolute values for each plotted on the percentiles. And the second one shows the latency reduction when comparing HP2 to HP3. For instance, for P99, there's a 60% reduction in last mile latency when comparing the 25 seconds for HP2 to the 6.5 seconds in HP3. When we first got this data back, we were extremely surprised, and I'm a little bit skeptic. We had hoped for a 10% reduction at P90 or higher, but we're blown away by these results. Since then, the data stayed quite consistent. We've continued to look for any possible bias or external factor that may be skewing the results, but have not found anything so far. Continue to look, but as I said, the data is looking extremely positive and in HP3's favor, which is, we hoped it was good, but we were very surprised it was this good. On the topic of trying to find skew, one of the first thoughts was to maybe look at the browser differences to see if something was up there. This chart splits the data that we just saw just by the browser and by Chrome and other group. As you can see, data is still quite similar. It's similar enough that I don't think you can draw any specific conclusions. Yes, you can see HP2 was a little bit higher in some of the cases for Chrome, but HP3 was a little lower. On average, I would say it's about the same, they even out, but nothing jumps out as a possible bias at first glance. Here is the same data split by request size. So you can see there's 4 KB, 8 KB, and 16 KB request sizes here. The data shows that HP3 obviously is still winning, but it's pretty much the same. A little difference in the 4 KB request size, but that also, I don't have it here, that also had a lower sample set size, since it was not very common that we sent that small. But again, nothing here to really call out as a significant bias or skew of the data. Same thing, but for response size. Essentially a couple more buckets here for response size. But again, the relative shape of everything looks pretty much to be the same. So from all the data we've looked at so far, HP3 has been the clear winner, independent of any other pivot that we've looked at. It has greatly reduced the last mile latency for OA. And at this point, I definitely recommend any service with the capability to upgrade to HP3 to do so. We have seen clear benefits with pretty much no downside so far. So the next step, I want to drill into the data a little bit more and try to explore where these improvements might be coming from. These two charts compare the same latency data when split by connection reuse. By that, I essentially mean that a request latency, does the request latency include the time it took to create a new connection, or did it simply reuse a connection? So is that latency including the handshake and everything else it takes to set up a new connection? Let's first actually look at the right graphs. These show the request latencies for requests that do reuse an existing connection. And as you can see, this data looks pretty similar to what we've been seeing in the last couple slides. And if you think about it, this makes sense because most requests do reuse a connection. Going back to what I said at the beginning, describing the scenario, this is because OA does use long-lived connections. These long-lived connections mean you have a high ratio of reuse. I think from what I've looked at the past, it's something like a 200 to 1. For every new request that creates a new connection, we reuse it for maybe 200 subsequent requests. So the data is heavily skewed towards reuse. So reuse looks pretty much like the same data as you see overall. Now let's look at the data on the left. As you can see, HP2 latencies go through the roof, while HP3 is largely unchanged. It's a tad slower, but not significantly, I'd say. And you're likely asking yourself, what the heck's going on here? Why is that so large? So let's take a look into those initial requests a little deeper. So these graphs show the latency for each layer phase of the request, with HP3 on the left for P99. This is just looking at the P99 case, and HP2 on the right. Obviously, the first thing that jumps out at you is the huge yellow layer for HP2, and that is the W3C DNS start layer. And you see a little bit of that on the left, but nothing like that on the right. So this is indicating time that is obviously before DNS start. So before even doing the DNS, which indicates such a client-side delay. Beyond that, though, even DNS is larger, and SSL layer is a little bit larger, and the connection layer, such as that light blue, is completely removed. But even if I filter out the DNS and the DNS start layers, you can see that things are a lot closer, but HP3 is still a clear winner here. In this particular case, about factor of half the cost. So some kind of reasons, conclusions here. HP3 doesn't have the connection layer because it's combined the handshake, essentially the SSL and the connection layer, at least what W3C refers to, into one, kind of a core part of the QUIC protocol design changes. So connection layer is completely eliminated, at least one round trip completely eliminated, so you get rid of that cost. SSL is a bit smaller here. That might be because of the design changes and just slightly more efficient integration between the networking code and the TLS layers. But going back to those pieces that we filtered out, a lot of that is because HP3 is effectively an upgrade from HP2, meaning HP2 happens first. So anything, whether it's a client-side cache or loading issue, anything like that is going to impact HP2, but HP3 gets the benefit of essentially a hot cache. Most of the time, that's always going to be loaded, and this is going to make HP3 look great relative to HP2. But it's not quite a fair comparison, because if you went straight to HP3 and never did the HP2, you'd likely see those same costs. We can do some magic and try to do this filtering like I have here, but overall it's a little more complicated, and we're still not even sure that produces an apples to apples comparison. So for the most part, we, for at least the OS scenario, kind of don't even look at the initial very much. Again, because we have long-lived connections, it's not super important. 1 out of 200 requests is not our priority. It's those other 199 requests. So definitely an area for us kind of to work with the browser teams to understand more of what's going on. Why are those kind of pre-network latencies so much larger than the network itself? Still a lot of investigation. There are a lot of possibilities. Even things like, say you've got a laptop going to sleep in the middle of some of these things, and then waking up, that'll skew clocks. And you're like, what? Like I'm at the extremely high latencies. I've seen DNS supposedly take 19 minutes. That doesn't quite make sense. So we're investigating those, trying to understand what's going on there and seeing how we can improve it. But kind of our temporary conclusions are, yes, this data is interesting, but not particularly useful for initial requests right now. We don't care too much. So let's look kind of at the other side. For reused connection requests, really there's two significant factors, layers here that take up latency for reused connections, but both of their definitions are a bit fuzzy. Request start is everything between having a connection and then sending the data out on the network. Generally, you'd expect time here to be minimal, but this time spent here can also be looked at as caused by head-of-line blocking, something like flow control. So you've got a connection, but you can't quite send something out because you're blocked by something. Unfortunately, we don't have any more information, such as exact reason codes to indicate what's going on here. This is still an area of investigation, trying to see if it is something like connection flow control, stream flow control, stream ID flow control, at least on the HTTP3 side, that we could improve, say by increasing our limits. We would want to know that to figure that out. So we have to work again to improve the telemetry, to get a better understanding. The app start is a similar scenario, in similar state. It's an estimate between the client and server's perspective of what things are attributed to the network costs. We still don't have a lot of information to break this down, but generally this is kind of the network cost bucket. So that brown, or sorry, grayish color is the app start, is the network costs. Again, as we've seen with everything, HTTP3 is a lot better here. The network costs are where HTTP3 has a greater improvement, at least when you're comparing these two P99. There's still a little bit improvement on the request start, indicating that it looks like head-of-line blocking was reduced. So still, things are better. We're still working to really narrow down why things are better, trying to understand exactly what's going on here. So we still have some work to do on the telemetry side to pinpoint and understand what's going on. When comparing the HTTP2 to HTTP3, at least in Windows, there are a lot of areas of improvements in the connection reuse scenario. A lot of them listed here. Some of these are protocol specific, some of these implementation specific, again, to the HTTP, at least Windows scenario. All these contribute to reduced latency data that we've seen in Exchange, but we don't have any data indicating how much each feature contributes. Like I said, I'm in the last slide, head-of-line blocking likely shows up as the request start chunk. So somewhere in there, those like independent stream data, FIFO stream scheduling for packet encryption, all would lead to reduced head-of-line blocking. And then the app starts, kind of the network, that's where better loss recovery and pacing improvements likely impacted. But we can't say how much each individual feature may or may not have helped things. We will continue to improve the telemetry and run additional tests to attempt to understand things better, like doing A/B tests, possibly turn off pacing, see if it makes any difference. But definitely a lot of opportunities to understand more and maybe even find additional areas of improvement to make HTTP3 even better. Kind of some other thoughts when we talk with folks about our Exchange Online deployment. No, we don't currently support 0RTT. It's not supported by the Windows TLS stack yet. We do support connection migration on the server side, but still have more work and testing to do in the area. It's not seen as a particularly interesting scenario yet, so there's not been a large focus on it, at least for the OA scenario. We do support MTU discovery, but don't have any telemetry for it. This is kind of a common theme. We've done a lot of work to add a lot of support, a lot of features, and now we're starting to do the telemetry side to kind of understand what's going on, to analyze what's working well, where we can possibly improve further. So I've been talking a bit, covered a lot on the exchange data. Before I move on to anything else, I figured this would be a good time to see if there are any questions.
Yeah, if you have any questions, please let us know in chat. For now, I had just a clarification comment. But when you say reuse connection, you mean a persistent connection, right? That doesn't have to do a new handshake. You don't mean a resumption.
Correct. So yeah, this is explicitly for those long-lived connections. It really comes down to no handshake was required for this request.
So in summary, the differences you see are almost all implementation efficiency, not network.
Can you clarify that?
So if you assume the user has the same network for H2 and H3, more or less, in aggregate, then the big differences you see are mostly the client-side stack that is less efficient for H2 than the implementation is for H3.
I don't know if you say less efficient necessarily. It's really hard to make concrete conclusions. Only thing I can say for sure is HP3 is performing better on HP2, independent of reuse or initial. The initial, it looks really good, but there are a lot of factors that might be skewing that. For reuse, it's definitely better. There are a number of reasons why it might be better, but we can't say for certain where the improvements are coming from. Whether it's client server, whether certain parts of the protocol are really making a difference, or maybe even implementation details. Like I showed, for HP3 we use the FIFO stream scheduling, whereas in the Windows HP2 stack we use round robin. There's so many contributing factors here. It's hard to say where the wins are really coming from. It might just simply be a combination of everything.
Yeah, that's something Miria also mentioned in the chat. She says maybe there's a bias because H3 stacks are just more up to date, while the H2 might have some out of date stacks. So older HP2 stacks that haven't been optimized as much as the H3 stacks.
Possibly. Though, and if you look at, say, on the client side, Chrome, we don't have it like per version of Chrome. I don't know if we can get that data. That might be interesting. Because if you assume all the clients, say all the Chrome clients are up to date, then your question is why are they using HP2 at all instead of HP3? So it's either going, practically it has to be that either the network isn't allowing it or they aren't using an updated browser. Those are the main two reasons that I would assume leads to kind of the decision between HP2 or HP3. Yet another area we need to dig into to see if we can get better telemetry to understand that. Because yeah, I mean, the data definitely shows this huge improvement for HP3 that we're still skeptical for. And we're trying to figure out, I mean, like, is it somehow all the good clients are using HP3 and all the bad clients are using HP2? And however you define good and bad, and that's the key thing that might be skewing the data. It's really hard to say. I mean, if anyone has any ideas or recommendations for how we might gather different telemetry or analyze even what we have so far to try to understand that, we're happy to take those and try to deploy it, gather some data, and come back with updates.
Excellent. We have one question from Florentin. Do the HTTP2 clients and HTTP3 have the same daytime behavior? So the same.
You mean like are they the same usage at same times of day?
Yeah, yeah.
Yes. From what I've seen, I'm going back
Yeah, so
to.
there's no skew to, like, let's say, mobile devices or corporate networks.
Yeah, and this is all browser clients. So the same browser client. So this is excluding mobile and desktop clients. They're not even included in the data that we've been looking at most recently. And at least the usage by time of day seems to be the same between HP2 and HP3.
Okay. I don't think we have any more questions for now.
Okay.
So please continue.
All right, thanks, Robin. So now to switch gears a little bit, we'll talk about various other products that have shipped using MS QUIC. Most people looking at QUIC immediately assume HTTP3 is the scenario. Robin even mentioned in his introduction that HTTP3 is the application scenario. But in Microsoft, SMB file transfer scenarios are hugely important as well for QUIC. And unlike HTTP3 scenario, where a large number of clients exchange smaller sized request responses, SMB has usually a few number of clients, maximum of 20 most of the time, but have a large bulk transfers, gigabytes in both directions at very high speeds too. So comparing HTTP2 and HTTP3, really conflicting scenarios have helped drive the design and implementation of MS QUIC to handle both of these efficiently. We've worked with the SMB team to ship SMB over QUIC, the server side in Windows Server 2022 Azure Edition, and the client in Windows 11. We've also been in cooperation with Visuality, such an external company, to add SMB support to their products, SMB over QUIC support, rather. The screenshot here is from a demo of their recently published Android app that's communicating with Windows SMB server in Azure. So like I said, a lot of work has been done on the implementation side to make sure SMB is kind of a first-class citizen in Windows. So that's why Windows has both SMB and HTTP3 as primary QUIC scenarios. My team also worked heavily with the .NET teams. That cooperation was actually the initial driving force to make MS QUIC open source. .NET has a requirement that all their dependencies be open source and ideally cross-platform. As a result of this work, .NET recently released their 6.0 release, which includes a preview client and server support for HTTP3. Both are cross-platform, currently supported on Windows and Linux. HTTP3 in .NET is already used in several different applications and APIs, including the Kestrel web server, the HTTP client API, and YARP, their recently released reverse proxy. .NET was also the first team to integrate HTTP3 into their gRPC solution, and they have active, I think, documents and requests out for how to integrate that into HTTP3 or into gRPC. And also, as I mentioned before, we work with a lot of different groups, and I can't really go through all of them, some because they're not quite ready to be public. But just a couple more here. We've worked to add support for Xbox Game Core, so game studios can make use of QUIC in their games. The audio video company NDI recently updated all their network communication to use MS QUIC in their latest SDK. We've even worked with a couple large media companies, some of which, again, not ready to be named, but DreamWorks is one that has allowed us to list them by name. So now I'm going to talk about our QUIC library itself, what it's taken to build and maintain this cross-platform QUIC library. As Robin mentioned at the beginning, I've been working on this for a while. In the last 4 years of working on this code pretty much full time, and a couple other folks kind of part-time at the beginning, full-time now. We've had nearly 1,500 commits since going open source, with several hundred more internally in the 2 years before that. Lots of code, with about half of that is production code, and a little more than half of that is the core protocol code that's platform independent, with the other half being kind of the platform abstraction layer, things like TLS, UDP, things like that. In the last year, a lot more time has been spent on quality and automation than actual feature work. Feature work had kind of wrapped up, not a lot of really fundamental changes, little things here and there. But we've built up a huge amount of automation that continues to provide a really high confidence in the quality of the code, which allows us to start working on even more things, allows us to accept external contributions without any kind of big fear of regressions. So as you can see, a lot of different automation has been onboarded and has run for every single change. A lot of cool features in the QUIC protocol, some of which we're still yet to fully implement. But at the end of the day, our consumers drive the priorities for our development. This results in putting most of our focus on making sure kind of the basics are as good as they can possibly be, make sure they're very solid. It's got to work, it's got to be interoperable, and it can't crash. Whenever you have something that runs in the kernel, crashing is generally viewed as pretty bad, considering it'll bring down the entire machine. So a lot of our time goes into automation to test these scenarios, both functional and performance testing. On one hand, though, this leaves a lot of room for external contributors to try their hand at filling the gaps at some of these features that we haven't quite gotten to fully implement. Lots of opportunities still there. When it comes to performance, like I said, that's one of our key priorities. After kind of getting the basics working, there's a lot of different ways to look at performance. Our primary focus generally is CPU usage, latency, and then network utilization. In the next couple of slides, we'll be looking at some data that's comparing CPU usage for HTTP and SMB scenarios. This will be for Windows user mode. So let's first look at the HTTP scenario. As I've already mentioned in the past couple slides, this tends to be with smaller payloads. This particular instance is 4K responses. Because of the small overall payloads that are exchanged, not a lot of CPU tends to be spent on crypto, but instead a large portion is spent on the UDP stack. Each send or receive UDP call isn't able to batch much because of the small payloads. So we end up paying the full cost of passing through the networking stacks for most datagrams exchanged. This flame graph is likely to be a little unwieldy for those not familiar with it, but generally represents the relative time spent on each call stack over the test period. Meaning the wider a column is, the more time was spent on that during a particular test. This particular flame graph is for the server side, and the server side for this was sending the 4K responses, so it is generally going to have more time spent on the send side than the receive side. So assuming you can read the tiny font, anywhere you see AFD, TCP/IP, or INDIS indicates that the call stack is generally network usage. And if you can see, a majority of these tall, wide columns are exactly that. It's not super important that you go through and look at all of them, but yeah, a lot of this is related to the networking stack. Conversely, if you look at crypto, right there in the middle, that kind of smaller column, you see some bcrypt stuff. That's pretty much all the crypto CPU. Not a lot of CPU spent on crypto, and the stack to the right of that, there's some EPIQ in there. That's the actual QUIC protocol logic, with one of those being almost entirely memcopy. So there's not a lot of CPU attributed to QUIC itself, not even a lot for crypto. Almost all the CPU usage ends up being taken up by various parts of the UDP stack, either on the send or the receive. This is just kind of the opposite side, the client side. It looks a little different because of how the protocol set up, both at like our kind of fake application layer, and because it's generally being a heavier receiver than sender. But again, you'll see a lot of INDIS, a lot of TCP/IP, a lot of AFD. The MLX5 is the Mellanox driver, because this was run with a Mellanox adapter network card. So again, a lot of UDP usage in the HTTP scenario. So next, though, want to look at SMB. Obviously, you can see this looks very, very different from the HTTP. And because unlike the HTTP scenario, SMB has the bulk throughput scenarios that send very large or send or receive very large bursts and sending huge payloads. These produce bursts of packets, at least from these particular tests, sometimes in excess of 40 full datagrams at a time. This allows the UDP networking stack to do a lot of batching, greatly reducing the overall costs of the CPU attributed to the networking stack. And now, because we've been able to reduce the cost of UDP, crypto becomes the biggest bottleneck. As you can see here on the left, there's a lot of bcrypt costs. Depending on the run, I've seen as much as, I think, 70% of CPU. I think that's usually in kernel mode, where UDP is even smaller. Huge amounts of CPU attributed to just crypto. So really, for these scenarios, the only way to improve them is to start pushing things to hardware. Offloading crypto to hardware is the only way you're going to start improving these bulk throughput scenarios. So again, this server side, because this is a download scenario, the server is mostly doing a send. On the client is doing a receive. You will see a large flame here for crypto, or sorry, for UDP on the right. But because of the parallelization that EPIQ does, the right stack is generally done on one core, the left stack is done on another. So the UDP receive is not actually a bottleneck here. But generally in networking, receive ends up being more expensive than send. That's why you see so much more networking costs here. So as I mentioned, we have all this automation. We have all this data generated and collected, measured every single commit. It's published automatically on our open source pages dashboard. This is kind of a snapshot from a week or two ago. You can go to this link, or you can go on our main GitHub page, and it has a link to this dashboard. You can go in and look. You can look at data for other platforms as well. Also, as I mentioned before, network utilization is a significant focus. For this, we have automation doing WAN performance tests. using GitHub Actions and a custom virtual network driver that allows us to simulate different network conditions. We regularly simulate over 1,000 different network conditions and measure the network utilization for every single PR, every single commit. This is still a work in progress. So while we do have the automation to run and collect the data, we haven't done anything with the data yet to automatically flag regressions, to find scenarios of kind of significant issues where we need to do investigations. So definitely an area we want to continue working on and improve. Beyond everything I've already talked about, there's so much more involved with building and maintaining a general purpose QUIC library. API design is really a big one with such a diversity of consumers in different environments and on different platforms. A lot of time has gone into creating an API that works well and could be performant for all these different scenarios. Writing an API that allows for Windows kernel mode callers to keep the data path at dispatch level for maximum performance, but also work when running on an Android or Xbox app can be tricky at times. Coming from a Windows-only world, going cross-platform was a big change. As I already mentioned, it was a must in order to support .NET scenarios, but it had a significant learning curve on our part. Moving everything from all our internal infrastructure out into GitHub was also a big task. Required us learning how to onboard things to Azure pipelines, GitHub Actions to automate this, but it really gave us a amazing opportunity to kind of take control and customize that to get way more coverage externally than we ever had internally. But it also required us to take ownership of things we didn't have to worry about before, such as managing releases and servicing of fixes. So with QUIC really starting to pick up steam, we have so many folks, both internal and external, getting interested in QUIC and what QUIC might do for their scenarios. Being open source allows us to work with more of those, and it's really exciting to work with them and see all the new things that are starting to come out. So we've come a long way, but there's still plenty to do, as Robin mentioned. There's still lots of stuff, both well-defined and open-ended research level work. Few things listed here specific just to MS QUIC, but this is by no means an exhaustive list. If you're interested, feel free to join us on GitHub. We have a good first issues tag, and we have a lot more advanced issues. And if you're really interested in helping shape the next generation of network systems, the Microsoft Core networking teams always have full-time and internship positions available, mostly based in the US. But we'd be happy to work with you. So I hope you all found this presentation useful. Be happy to answer any more questions that you might have. Let me go.
Yeah,
chat.
I very much enjoyed the keynote. Thank you so much, Nick, for all the excellent data and insights. And can I just say that I really appreciate you digging deep into some of the data, right? You're not just showing the aggregates, you're really digging into different slices of the data and trying to find where the biases are and all these things, and things that are sadly still missing in a lot of academic work on QUIC as well. So it was really a masterclass in how I think it should be done. If anyone here has any questions for Nick, please type them in chat or let us know if you want to ask them in person. That's also still possible. Otherwise, it will just be the next 10 minutes of me asking questions that I find interesting, which is a perk of being one of the chairs, obviously. The first question I had when you were talking about the flame graphs was, how much optimization has gone into the UDP stack for now? It's like, is this like the best we can do at this point, or is there still much room for improvement that you've found?
At least for Windows, we've done a lot really over the last maybe 3 or 4 years, really kind of in parallel with our QUIC work. We've always known that UDP wasn't heavily optimized. It wasn't the primary scenario. TCP always was when you were talking about really performant things. So we've done work on all the batching stuff, doing kind of the normal nitty gritty of run your scenario, find a bottleneck, fix the bottleneck, go to the next one, doing that over and over. The latest Windows Server and Windows Client have all those fixes and improvements. But yeah, we have kind of come up to a limit of what you can do. Windows has to support a number of what you might call legacy scenarios. And because of all these legacy things, different, for instance, entry points for things like antivirus or like Windows Defender, so many different points in the networking stack cause delays. And we've hit a point where the only way to make things faster is to bypass it. So looking at things like DPDK or XDP that bypass the networking stack is kind of the next step. All right, for those cases where you absolutely need even better performance, those are going to be the ways we have to go.
Yep. So you're going to bypass the kernel inside of the kernel.
Well, not necessarily in the kernel. So maybe we'll see about that. A lot of stuff we actually try to focus on the client or on the user mode side, because outside of Windows scenarios, everyone else's scenarios practically live in user mode. So for HTTP, I think it's good enough already. Generally, there's still some work we need to do, but while yes, there is still a lot of CPU usage spent on UDP, practically we haven't found it an issue. For instance, in our Exchange scenarios, networking costs before this, I think it was single-digit percentage, like 1 to 4% of all CPU was spent on networking. So even if we doubled that, it was not a significant issue, and we didn't double it. I don't remember what the numbers are, but at the end of the day, the CPU costs were not really a factor. So it's not a huge primary focus to try to make that better in the kernel mode. SMB is a little different, but SMB over QUIC, the primary scenario actually is over the internet, not over kind of a local network or a corporate network where you might be able to send those huge speeds. So internet, maybe a gigabit is really the highest you can expect to ever achieve, and we have no problems hitting that. We can get 4 to 8 gigabit depending on the hardware already. So in the end, practically, we're pretty good for the existing Windows scenarios. In user mode, the open source stuff, that's where you get a much larger variety of things. Some people really want the huge throughput. Some people actually want the really low latency, microsecond latency. All these different scenarios continue to drive design changes, prototyping, and then finally actual implementation changes to support these.
All right, thanks. Very interesting additional data as well on the CPU usage. I have a question from Timo, which I have to really focus to get correctly. Is DPLP MTUD, so the fancy MTU discovery, is it enabled by default in the stack? And do you have any? You said you don't have any data, but do you have other anecdotal experiences with it?
I'm 90% sure it is enabled by default, and all the data that I've shown you today will have that enabled. So as you point out, I already mentioned we don't have any additional data, but it doesn't seem to be hurting us, at least relative to HP2. HP3 is still much better. I know I've followed the Slack conversations around this, and I know there are there are dragons out there. When you enable it, so far we haven't seen any significant issues that we know of.
Excellent. We will have more discussion on this with the paper later today. Then Florentin asks, do you think some of the Microsoft's apps would benefit more from the QUIC design than others? So you've mentioned HP3 now and SMB. Are there other things that you think would really benefit from QUIC?
Yeah, I personally, like my goal is to make at least MS QUIC capable or a reasonable alternative or upgrade, whatever you want to call it, for anything that needs to do secured network communication. Whether they had a custom UDP or TCP-based protocol before that might have or might have not used encryption. As I talk with all these different groups, it's amazing how many things out there like, oh, we don't need encryption, we don't really care about it. I'm like, well, then your traffic can easily be intercepted and modified, and but my goal is to make QUIC an option for all of them to upgrade, and pretty much provide a solution for any kind of, well, you might add extra latency here, or you might not be fast enough. So my goal is to make MS QUIC a replacement for every single one of those. I personally think anything should be capable of upgrading. There are definitely things out there that would benefit, and maybe maybe not functionally, but just in code complexity. A lot of things out there that do unreliable, for instance, have a reliable channel. So a lot of things you'll see application protocols that they've got a TCP connection and a UDP socket, and they're doing both. There's a lot of synchronization, a lot of complexity on the client and server to synchronize these things. Moving to a QUIC-based solution where you have, at least at like the code level, the API level, you have one connection, you have streams, you have datagrams, but they're all multiplexed into the same object. It can really simplify code. And in the end, it's going to be more secure, and more performance, because all we do every day, all the time, is just try to work and make these things more performant. Most of the people we work with, their usage of networking is kind of like a side job to them. Their goal is to make the application protocol. Oh, they had to make some networking code along the way, and they got something that works, but maybe it's got caveats or it's not the best. Whereas like my team's job is just work on this and make it as good as it can. So we can make improvements to that. So definitely, I think lots of things. Like I said earlier, NDI, which is essentially an SDK for exchanging audio and video, they moved to QUIC. They actually saw some interesting unexpected benefits. They had, for instance, some local networks where TCP actually didn't work well or not at all because of middle boxes doing things in the middle. Moving to QUIC, everything started working. So I wouldn't use that as a selling point, but there have been examples already where that's been the case.
All right. Again, fantastic additional data. Last question in the chat is from Luca from Facebook, and he asked if indeed the crypto is a big cost for the transfer. Have you evaluated any sort of hardware offload?
Yeah, we've started looking at it. I've had like some initial email discussions with some folks, I think like at Intel or Mellanox maybe, but we haven't had any customers really driving that yet. So kind of going back to that priority slide, in the end, there's lots of neat stuff to work on, but really our customers, so the people with the money decide where the work goes. And we haven't had anyone really asking for that yet. So not any real work has been done at that. We support a knob in QUIC to essentially turn off encryption for testing purposes, to really get an idea of like, what happens if crypto was completely offloaded and free? What kind of rates could we get? So we've done some of that work to get an idea, but we haven't done anything official at offloading.
Yep. Lucas says thanks, so that's a good answer, I guess. We are officially now in the 15-minute break before the first presentation. So if people wanted to have a bathroom break or anything like that, please do that now. I myself can't really hold myself in because I have one question that I really want to see answered. So it's the last one I'm going to ask, I promise. How do you firewall or protect against DDoS your large scale deployments now? Because a lot of firewall vendors, especially for smaller companies, they just say disable QUIC. We don't support QUIC yet. Did you do like a custom firewall implementation for this, or do you use a commercial offering that does this correctly, or what were the challenges there?
So I'm inside MS QUIC itself. We've actually got a lot of logic built in to try to handle several of these scenarios. I actually built a tool I call QUIC Attack, just to try to test some of these, try to spam an endpoint with as many initial connections with different connection IDs as possible, as fast as possible, things like this. And I've taken those tools and directed them at our servers running Exchange. And with the implementation logic we have in MS QUIC, I wasn't able to make any significant impact on the servers. Isn't it? The implementation handled it itself. Obviously, if you can generate enough UDP traffic just to overwhelm the networking stack, that's a different story. But at least at the QUIC layer, what we've seen so far is the code we have in the QUIC stack itself is able to handle that stuff. So we haven't had to have something separate yet. That doesn't mean we're perfect. I've came up with some attacks that were easy enough to implement. There might be some really complicated ones that require a very dedicated attacker to build up. But majority of your attackers are going to look for something that's quick and easy, and then just try to spam it off. So far as I can tell, we're pretty well defended against those just by our implementation.
So on the firewall side, you basically just open a UDP port, and that's it, I assume.
Yeah, I think Azure and stuff have some stuff kind of generically for UDP just by default, but there's nothing QUIC specific.
Okay, that's, at least for me, very, very interesting to hear that it works. All right, with that, we don't have any more questions, and we have a 10-minute break still remaining. So please join me in giving Nick a very well-deserved virtual applause. Without webcams, it looks silly, but whatever, please do that. I at least thought it was an amazing keynote, exactly what I wanted when I asked you, Nick. So thank you so much for that. I have many more questions. I will just add them in the Slack, the SIGCOMM Slack. So if you wouldn't mind taking a look at that during the day and maybe answering some of those, that would be great.
Definitely happy to. And thanks for having me, Robin.
No, the pleasure was all ours.